Welcome to our Unit 2 review. Let's take a look at number 1. It says the diameter of the moon is 3,474 kilometers. Part A says find the circumference of the moon. Assume the moon is a perfect sphere and give your answer to 2 decimal places. Okay, so always pay attention to the directions about rounding. So to find the circumference of the moon, I'm going to use the formula diameter times pi. We're given the diameter, so we multiply that by pi. This is what your calculator would show you. But since the directions said, let me erase this extra line here. Since the directions said, there we go. Since the directions said correct to 2 decimal places, here's the first decimal place, that's the 10th place. Here's the second decimal place, that is the 100th place. Then if you look at the third decimal place, it's only 2, so we don't round up. So here's your final answer, 10,913.89 kilometers. Then point B says, write down your answer in part A, correct, let me circle that. So your answer in part A, we're going to write that answer correct to the nearest 100. So here's the tens place, here's the ones place, here's the tens place, and here's the hundreds place. So this is a lot closer to 900 than it is to 1,000. So to the nearest hundreds place, we'd have 10,900 kilometers. And then part C says write down your answer to part B. So take this number and put it in the form A times 10 to the K, where A is between 1 and 10 and K is in integers. In other words, put it in standard form. So you're not going to go to 3 significant figures. You're going to take this number and write it in standard form. So we'd move the decimal point here. So we'd have 1.0900 times 10 to the 4th, because we'd have to move that decimal point 1, 2, 3, 4 places to get back to this number. Okay, and then on both of these, don't forget your units. Number 2 says Tommy is making a right-angled triangular table to place in one of the corners of his room. The 3 sides of the triangle have lengths 16 centimeters, 19 centimeters, and 30 centimeters. Show that this triangle is not right-angled. So you're going to take the largest side, which is 30, and square that, and then compare it to the sum of the squares of the other 2 sides. Well, when you do the arithmetic, you see that the biggest side squared is not equal to the sum of the squares of the other 2 sides, so it is not a right triangle. Number 3 says, an arc of a circle with radius 8 centimeters has a central angle of 22 degrees. In part A, we're going to find the length of the arc. So here's a picture of our circle with an 8 centimeter radius and a central angle of 22 degrees. So the arc length would be this arc that's cut off by that 22 degree angle. So to find arc length, instead of the arc length is going to be a portion of the entire circumference, and that portion will be 22 3/60ths of the circumference. We find the circumference by taking 2 times pi times the radius. So this is all arithmetic you can do on your calculator. In the absence of rounding directions, we'll default to 3 significant figures. So we would get 3.07 centimeters. Don't forget about your units, okay? And then part B says, find the area of the sector with central angle 22 degrees. So here's a picture of that. We've got our 8 centimeter radius, the 22 degree central angle. So this yellow portion of the circle, it's called the sector. Now it would be a portion of the entire area. You'd find the entire area by taking pi times the radius squared, but I don't want the entire area. I just want 22 3/60ths of it. So again, this is all arithmetic done on the calculator. Rounded to 3 significant figures would be 12.3 centimeters squared. Notice that arc length is in normal linear units, and the area of a sector will be in square units. Then number 4 says, Bambi has a triangular orchard, ABC. The length of side AB is 124.5 meters. The length of side BC is 230.8 meters, and the angle between side AB and BC is 128 degrees. So we're first going to find the area of Bambi's orchard, and then we will give our answer correct to the nearest integer. So I've drawn a picture of the orchard with everything labeled. So when we have 2 sides and the included angle given, that's when we can use this formula to find the area of the triangle. 1/2 times the product of the 2 sides and then multiply that by the sine of that included angle, okay? Make sure your calculator is in degree mode. Do all the arithmetic in one step. This is what the calculator would show you, okay? But you don't need to write that down. I just am showing you what the calculator would say. We're going to first go to the nearest integer. That's the nearest whole number. So since this tenths place is 5, that's going to bump this ones place up to 2. So we'd have 11,322 square meters, because this is an area problem. And then part B says take that answer and write it correct to 1 decimal place. Well, here's our first decimal place. That's the tenths place. Since the hundredths place is 8, that's going to bump this 5 up to 6. So we get 11,321.6 square meters. Okay, then number 5 says a triangular plot ABC shown in the diagram below has an angle A of 80 degrees, an angle C of 32.5 degrees, and a side BC of 325 meters. So I have labeled all of that. Now, notice that we have one angle that's missing, so let's go ahead and label that. Just take 180 minus 80 minus 32.5, and we'll get 67.5. So part A says, let's find the length of AB. So since AB is opposite angle C, I'm going to call it little c, and this is a good time to use the law of sines. So let's do this. To find C, let's look at the angle opposite C. We'll take the sine of that angle, put it over C, and then set that equal to the sine of 80 over 325. So there's our equation using the law of sines. And when we cross multiply and then divide, we're going to get that C is equal to 177 meters. Okay, and that's a linear unit, so there's part A. Okay, then part B says find the size of angle B. Oh, we've already done that. We found the size of angle B, so that's taken care of. So and again, the way I did that is I just took 180 degrees minus the two angles that were given, 32.5 degrees minus 80, and that's going to give me that 67.5 degrees. Okay, and then part C has a typo. It's supposed to say find the length of AC. I think I fixed that on your copy of it. Okay, so once again, to find AC, since AC is opposite angle B, let's call it little b, okay? And so to find that side, let's use the law of sines again. So let me use let's go ahead and use the, let's see, we're going to use the sine of, let's use the green, the sine of 80 over 325. And then let me get another color highlighter here. Let's see, how about, I guess this color. How about red? So this over this. So we're going to take the sine of, so let's start with the green. That would be the sine of 8, oops. Sorry about that. Let me get a pen. Okay, the sine of 80 degrees over 325 is equal to, now let's look at the red, sine of 67.5 degrees over B, which is what we're looking for. Cross multiply and divide to 3 significant figures. We're going to get that B is 305 meters. Okay, so now the last part says find the length of fencing in meters necessary to fence the triangular plot. Okay, so we were given one side. We have found the other two sides. So we'll add those 3 sides together. And when you do, you would want to use exact values. I know it's tempting to use your rounded values, but go back and use those exact values. And so we're going to take the 325 that were given, plus the value we got for B, plus the value that we got for C. So hopefully you have those values stored in a variable. And so you'd add those all together, and we would get, let's see, 807 meters to 3 significant figures. Okay, number 6 says a box designed to be used as a juice container has dimensions 4 centimeters by 5 centimeters by 7 centimeters. Find the volume of the, another typo. Sorry, there's several typos on this document, and I apologize for that. Let's change that to the volume of the, I'm going to call it the cuboid, because that box would, since by the dimensions we're given here, we're going to assume that it's a cuboid. Okay, so to find that volume, we're just going to take the length times the width times the height. So that would be 4 by 5 by 7. So that's going to give us 140. Now this is volume, so it would be cubic centimeters. Okay, and that's an exact answer. You didn't have to worry about significant figures on that one. Then part B says, well, then it goes on to say the juice container is expected to hold 120 cubic centimeters of juice. So that would be the exact expected value, but a sample container is found to hold 110. So that would be an approximate value. Okay, determine the percentage error. So let's just review that formula because I'm seeing some mistakes on this. So the formula looks like this. It's V sub A, which is the approximate value, minus the exact value, all divided by the exact value. Take the absolute value of that, so your answer should not be a negative answer, and then multiply it by 100. And then I like to put all parentheses around all that and put a percent symbol, because you must have that percent symbol in your answer for it to be correct. Percent means per 100, so if you leave the percent symbol off, that's a different number. So in this case, our approximate value is 110. The exact value is 120. Take the absolute value of all that times 100. Grab a calculator, work that out, and you're going to get, let's see, where's my answer? To three significant figures, 8.33, and don't forget your percent symbol. Okay, then number 7 says a petroleum tank is in the form of a cylinder with radius 5 meters and the volume of the tank is 700 cubic meters. So in part A, we're going to find the height of the cylinder. So let's look at the formula for the volume of a cylinder. We would take the volume of the cylinder by taking the area of the base and multiplying that by the height. So let's plug in what we know. We have a volume of 700. We have a radius of 5, but we do not know the height. Okay, so to solve for h, we're going to take 700 and divide it by pi times 5 squared. So we'll do that on the calculator, and height turns out to be, to three significant figures, 8.91 meters. That would be just a regular linear unit. Okay, then part B says find the total surface area. So total surface area of a cylinder is going to be 2 pi RH. That gives us that curved surface area plus the areas of the two bases that are both triangles. So now that we know what h is, I'm just going to go ahead and write 2 times pi times our radius was what, 5 times h, knowing that, remember, I have an exact value for h, okay? I have that exact value, so I don't want to put a rounded answer in there. I would rather that you store that in a variable h and then plug the exact value in. Then let's keep going. Let's see. Then we're going to add 2 times pi times 5 squared. Okay, so grab a calculator, multiply that all together, and you're going to get to three significant figures, 437 meters squared. And again, there were no rounding directions, so that's why I'm defaulting to three significant figures. Then part C says, find the amount of paint necessary to cover the surface area of the entire tank if 1 liter of paint covers 11 square meters. And then this is really extra information that we don't need. All we need to do is take our total surface area, which was our answer to part B, and then we're going to divide it by 11 meters. So if we take total surface area divided by the amount of tank, the fact that 1 liter covers 11 square meters, that division will give us the number of liters. Now, I'm going to write surface area, because remember, that is an exact value. I don't want to put 437 in because that was rounded. So if I take total surface area and divide it by 11, okay, so that's going to give us, now it's going to give us 39.7 liters. Now, if you put that for an answer, that's to three significant figures, I would count that correct. However, if you were actually going to go to the store and buy paint, you're not going to say, I need 39.7 liters. They're not going to sell paint to you like that. So I would accept either of these answers. I kind of prefer the second one because that's how you would actually buy paint, but either answer would be acceptable in this case. Okay, number 8 says the Ultimate Volleyball Factory produces volleyball balls with a radius of 21 centimeters. Each ball is tightly packed in the box so that it touches each side of the box. To protect the ball, the box is filled with foam. So we're going to find the volume of the box. Okay, so to find the volume of, now that box is going to be a cube, so to find its volume, we just need to take each edge and square it. Now, if the radius is 21 centimeters, that means that the diameter of the ball would be 42, and that would be that 42. The diameter of the ball is also going to be the length of one of these edges, okay? Because remember, the ball touches on all sides. So to find the volume, I'm just going to take 42 and cube that, and that's going to give me 74,088. This is volume, so it's going to be cubic centimeters. That's an exact answer, so you didn't have to worry about significant figures on that one. Then part B says, find the amount of foam needed to fill the box. Well, what we're going to do is take that volume of the box, that 74,000, and notice this was an exact value, so I can go ahead and use that, 74,088 minus the volume of the ball, which the volume of a sphere, let me just write up here, volume of a sphere is 4/3 pi r cubed. So that's going to be minus 4/3 times pi times the radius of 21 cubed. Okay, so that is arithmetic that we can do on the calculator, and we're going to get 35,295.61. Now that's, and there's more digits there, but that's what the calculator would show us. There's nothing about rounding, so we need to go to three significant figures. So here's our first significant figure, there's the second one, there's the third one. So this answer, since we can't put it exact, we'll go to three significant figures, and that's going to be 35,300 meters cubed. Let's see, number 9 says a regular rectangular pyramid. Now a regular rectangle would be a square, so we could call this a square pyramid with base side 1.5 meters is made of a transparent acrylic material with a volume of 1.6 meters cubed. It is to be used by a museum to exhibit a piece. And then it says a cone with a radius of 0.80 meters and height and apex. Apex means this vertex. Height and apex, the same as the pyramid, is carved out to make space for the exhibition piece. So part 1 says show that means you need to show some work. Show that the maximum height of the museum piece that can be encased by the pyramid is 2.1 meters, correct to 1 decimal place. So to find that, since we were given the volume, let me underline that. Since we were given the volume, we're going to use our volume formula. Okay, which says, let's see, the volume, oh dear, hold on. Okay, so the volume of a pyramid is going to be 1/3 the area of the base times the height. So in this case, that's going to be 1/3 times 1.5 squared times the height, and remember we're given the volume is 1.6 cubic meters. So that means our height is going to be 1.6 divided by, let's see, I need to multiply both sides by 3, right? So it'd be 3 times 1.6 divided by 1.5 squared, okay? So that's our height. Now, if you do the arithmetic on a calculator, you will see that that height to 1 decimal place, remember 1 decimal place is what we were asked to show, is 2.1 meters. Okay, so we've shown that. And then part B says, determine the volume of acrylic material that has not been removed from the pyramid, so that empty space. So to find that volume, we will take the volume of the pyramid and we will subtract the volume of the cone, okay? cone. Okay, so the volume of the pyramid we were given is 1.6 cubic meters. Then we're going to subtract the volume of a cone. The volume of a cone is 1/3 the area of the base, which is pi r squared times the height. So that would be 1.6 minus 1/3 times pi times our radius was 0.80 squared, and then times the height. Now remember that height, I don't want to use a rounded value, so I could either put in h here where I have the value stored in h, or I could just type in the whole expression, which is 3.16 over 1.5 squared. I don't know why I said type in, I'm writing, okay? So we'll do all that arithmetic in one step, and then to three significant figures, we're going to get 0.170 meters cubed. That's how much of the acrylic material that has not been removed from the pyramid. In slide number 10, we're given a parallelogram ABCD. And the first thing we're asked to do is to find the length of AC, which is a diagonal. So I'm going to draw that diagonal. Okay, it looks like that. And then what I'm going to do is I'm going to focus in on, let me color a triangle. I'm going to focus in on this yellow triangle. And one thing I should have done before I drew the diagram is to help you recall that in a parallelogram, remember, consecutive angles of a parallelogram are always supplementary. So if this is a 41-degree angle, then that means angle B is going to be 139 degrees. Okay, so let's go ahead and label that, draw the diagram. Now in that yellow triangle, we're being asked to find AC. I'm going to call it little b because it's opposite an angle B. You can call it anything you want, but I usually try to name it by give it the name that's the same as the angle opposite, but just use a lowercase variable. And then, so in that yellow triangle, notice that we're given two angles and an included side. This is the perfect time to use law of cosines to find B. So to find B from law of cosines, I know that B is going to be equal to the square root of the sum of the squares of the other two sides. So that would be 10.1 squared plus 15.9 squared minus 2 times 10.1 times 15.9 times the cosine of that included angle, which is 139 degrees. So if you don't remember the law of cosines, remember it is in the formula booklet. You can always look it up, okay? Okay, so that's arithmetic that will be done in one step on your calculator. So we get that B will be, to three significant figures, 24.4, and that's a linear length or a linear measure. So we use linear units. That's going to be just regular centimeters, okay? And then point B says, find the angle that line AC makes with line AD. So here's line AC, and here's line AD. So let's call that angle theta. I'm going to label it. That's called theta. And then let's also label, you'll recall in a parallelogram that opposite sides are congruent and also opposite angles are congruent. Let me write that again so you can actually read it. That's supposed to say 10.1 centimeters. So this is a 139-degree angle. Okay, so to find theta, we could use law of sines. Let's see if we can make it work. So I'm going to grab a highlighter, and I'm going to highlight, let's see, theta and the side opposite it. And then remember, we know what B is now. So let's highlight B and then the angle opposite B. So that's perfect setup for law of sines. So let's see, so part B, I'm going to start with the blue. I'm going to say the sine of theta over, let's see, 10.1 is going to be equal to the sine of a 139-degree angle over B. Remember, B is not unknown. B has a value. It's all this stuff, right? That hopefully you have that stored in your calculator, okay? So now, let's cross multiply. Let me show a little more algebra this time. So if we cross multiply, we're going to have B times, I'm going to change colors. Hold on just a second. Blue, okay. B times the sine of theta is equal to 10.1 times the sine of 139 degrees, okay? We will divide both sides by B, okay? And then we'll get that the sine of theta is equal to 10.1 times sine of 139 degrees, all divided by B. And again, remember, B is a constant. It's not unknown. So that means that theta is going to be equal to sine inverse of 10.1 times the sine of 139 degrees, all divided by B, which we figured out in part B, or sorry, part A. So now grab your calculator, make sure it's in degree mode, and we would get that theta, and go ahead and calculate that. Theta turns out to be, to three significant figures, 15.7 degrees. And then part C says find the area of the parallelograms. Remember, the area of a parallelogram, this yellow triangle is half of the whole parallelogram. We would know how to find the area of the yellow triangle. So to find the area of a parallelogram, it's the same formula as the formula for the area of a triangle. We'll just take out the 1/2. So to find the area of the parallelogram, let's use these two sides and the included angle. So we'll just take 10.1 times 15.9, and then we're going to multiply that by the sine of that included angle. Again, make sure your calculator is in degree mode. And to three significant figures, we're going to get 105 centimeters squared, because this was an area problem. Now let's take a look at number 11 that says a hemisphere, which of course is half of a sphere, has a radius of 3 centimeters and a cone has a radius of 6 centimeters. Given that the volume of the hemisphere is twice the volume of the cone, show that the curved surface area of the cone is equal to 113 centimeters squared to three significant figures, okay? So to find surface area of a cone, let's just recall that curved surface area of a cone is pi times the radius times the slant height, okay? So slant height, remember, would be the measure from the vertex to the edge of the base, okay? That's going to be our L, okay? Oops, I meant to do that with a pen. Hold on. That's going to be L, okay? And then we're going to find H. Once we know what H is, since we know the radius is 6 centimeters, then we can use Pythagorean theorem to find L and to plug into this formula to get that curved surface area. Okay, but we have a little bit of work to do to find L. So let's start with the fact that the hemisphere, that the volume of the hemisphere is twice the volume of the cone. So let's start by finding the volume of the hemisphere. To find the volume of a sphere or a hemisphere, all you need to know is the radius. So let's start with that. So the volume of a hemisphere, okay, is going to be 1/2 times, because I'm taking half of the volume of a whole cone, so that's going to be 1/2 times 4/3 times pi r cubed. Or in this case, that would be 1/2 times 4/3 times pi times a radius of 3 cubed. Okay, so we will do that arithmetic, and let's see. Let's see. I'm going to cancel a 2 here, and then I'm going to cancel a 3 with one of these. So I end up with 2 times pi times 9, so that's going to be 18 pi. Okay, so that is, and that's in centimeters cubed. Okay, so that's the volume of the hemisphere. Now we're told that the volume of the hemisphere is twice the volume of the cone. So what volume would I double to get 18 pi? That would be 9 pi. So that means that the volume of the cone is 9 pi, and that's going to be centimeters cubed, okay? Remember, we were told that the volume of the hemisphere is twice the volume of the cone, or another way to say that would be the volume of the cone is half the volume of the hemisphere. So the volume of the cone is 9 pi. Now, to find the volume of a cone, remember a volume of a cone is going to be 1/3 pi r squared h. Okay, so since I know the volume of the cone, I can put 9 pi in for that. And I also know the radius. The radius of the cone is 6. So now you see I just have this one unknown h. I can solve for h, can't I? And remember we wanted h because I needed h to find the slant height so that eventually I can find the curved surface area of the cone. So now let's do this. Let's cancel pi from both sides. And then I'm going to multiply both sides by 3 and divide by 6 squared. So h is going to be, let's see, I have a blue pen. Okay, h is going to be, what did I say? I'm going to multiply both sides by 3, so it'd be 27 on top divided by 36, and that reduces to, let's see, 9 goes into both of those, that reduces to 3/4. So now we're getting closer to finding the curved surface area of the cone, but before we do that, I realized I have a typo I need to fix. And that is this 113. Now your copy doesn't say this. It says 113. It's supposed to be it's supposed to be 114. So my apologies for that if that's caused any confusion, because that's going to matter here in a minute. So what we're going to do next, if we're going to take pi times r times L, we already know what r is. We need to find out what L is. So we're going to use this little right triangle here where we now know what h is. It's 3/4. And we know what the other leg is. It is 6. Okay, so using Pythagorean theorem, that hypotenuse squared is going to be equal to h, which is 3/4 squared plus 6 squared. Okay, so that means L, that's a squared, L is equal to the square root of 3/4 squared plus 36 squared. You can either write 36 or 6 squared, doesn't matter. And then I'm not even going to evaluate that. I don't need to. I'm just going to put that all into my calculation. So to find the curved surface area now, finally, I can take pi times the radius of 6 times L, which is the square root of 3/4 squared plus 6 squared. And if you do that calculation on your calculator to 3 significant figures, you're going to get 114. And this is surface area, so that's going to be centimeters squared. Okay, number 12 says, OB and PQ are two sides of a long straight road. Thanks for the description. Okay, Sarah crosses the road from O to A and to visit a friend, and then crosses back from A to B. She finishes on the same side of the road as she started, but is 60 meters further along. And the question is, find the width of the road. So here's our road. Here's the two sides of the road. We need the width. So to find that width, I'm going to drop a perpendicular from A to the other side. And then what I've done is I've created a little, whoops, hold on, I meant to use a highlighter there. Oh, nuts. Let me fix that. Okay, what I've done is I've created a little right triangle, okay, where I am trying to find the one leg. Now, the leg I'm going to be looking for is this, because that's the width of the road. Now, normally I would call that by the name opposite the angle, but I don't want to use O because it looks too much like a 0. So I'm just going to call that X. Okay, so let's find X. Now, I can find X using right triangle trig if I knew this hypotenuse. So to find the hypotenuse, let's look at the big triangle, okay? And let's see if we can use either law of sines or law of cosines. So I'm going to call this hypotenuse of the yellow triangle, I'm going to call it little b because it's opposite this angle B, okay? And I think I have enough information to use law of sines as soon as I figure out what this angle is. So in the big triangle, I can take 180 minus, what is that, 60 minus 35 to get 85 degrees. So this angle is an 85-degree angle. Oh, that's hard to read. Let me write that so you can read it a little better. 85 degrees. Okay, so now let's find some parts that we could use for law of sines. So to find B, I'm going to use the angle opposite B. And then we can use, let me get a different color. How about red? Then we can use this 85-degree angle and the side opposite it. Okay, so step one is we're going to find B using law of sines. So I'm going to take the sine of, I'm going to do greens, the sine of a 35-degree angle over B is the same as the sine of an 85-degree angle over, what is that, 60, okay, over 60. I should have expanded this, made this bigger so we could read it. Okay, so we would cross multiply and solve, and we would get, let's see, B is going to be, and I'm not even going to calculate it because I want an exact value anyway, so B would be equal to the product of 60 and the sine of 35, all divided by the sine of 85. So that is just cross multiply and divide. Okay, so now if I look at my little triangle, I now know what B is. And with respect to, let's see if I can write on this tiny diagram. I should have made it bigger, sorry. With respect to this 60-degree angle, okay, I am looking for the opposite side, and I now know the hypotenuse, don't I? So, since I am looking for the opposite side, and I know the hypotenuse, and I know the measure of the angle, this would be a time to use inverse sine. Remember, opposite over hypotenuse is sine. Oh, by the way, let me say this. This is the appropriate time to use SOHCAHTOA, okay? I'm looking at a right triangle. Make sure you only use sine, cosine, or tangent ratios if you're dealing with a right triangle. If it's a non-right triangle, you can't use sine, cosine, or tangent. That's when you use law of sines or law of cosines. Okay, so now to find x, I'm just going to write a trig ratio. I'm going to say the sine of that 60-degree angle is equal to the opposite over opposite over the hypotenuse, okay? Remember, I know what B is. Let me do this. Remember, B has a value. It's this, okay? So to find x, to find my width of the road, I just need to take, well, here, let me turn it around. To find x, I would multiply both sides by b. So x is just going to be sine of 60 degrees times b. So in my calculator, I'm going to type in sine of 60 degrees times b, which was 60 times sine of 35 all over sine of 85. Okay, do all that arithmetic in one step. And to three significant figures, my final answer is going to be 29.9 meters. Okay, number 13 says a paving slab consists of 3 composite parts. A composite figure is a figure made up of pieces, okay? So it has 2 identical sectorial areas. Those are areas that are sectors, and 1 isosceles triangle as shown in the diagram. So we're going to find the total area of the slab. Now I'm going to make this bigger so we can see it better. Oh, now my old eyes can actually see that. Okay, so let's start filling some stuff in. First of all, I've got another 35. Remember that we were told the sectors are congruent. So both of those angles would be 130, would be 35 degrees. And then I think you can see if I were to put a protractor over all 3 of these angles, they're going to total 180 degrees. So that makes this angle 180, not 180 degrees. It's going to be 180 degrees minus 70, which of course would be 110 degrees. Okay, so now let's kind of write a little formula to find the total area. So let's start with the 2 sectors, okay? So remember, to find the sector of a circle, we would take 35 3/60ths times pi times the radius squared. Now, that would give me the area of one of those sectors. Let's highlight them so I can, well, it's going to take a while. Sorry to color this. So let's make one sector yellow. Sure, there's a way to get a fatter highlighter. You can fast forward through this part if you want while I'm coloring. I've never been good at coloring, but I'm kind of staying in the lines, so that's good. Okay, so there we go. So there's two of those yellow sectors, so that means I'm going to put 2 times that. So that's 2 times the sectors, plus we're going to find the area of a triangle. So I'm going to write, let's see, where's my, okay, plus the area of a triangle. So to find that area of the triangle, I'm going to take 1/2 times r times that included angle, which is, excuse me, times the sine of that included angle, which is 110 degrees. Okay? All right, so it looks like we have a little bit of work to do because we need to figure out what r is. So let's look at in the white triangle, and that white triangle is isosceles, which means that these base angles are congruent, aren't they? Okay, so if I take 180 minus 110, that gives me 70 degrees, which I will split equally amongst these two angles. Okay, so now it looks like we can use law of sines to find r. So let's do this. Let's use the 110 degree angle and the side opposite that, and then pick one of these 35 degree angles and the side opposite it. So using law of sines, then I can say that the sine, oops, let me get a pen, not a highlighter. Okay, the sine of a 35 degree angle over r is the same thing as the sine of that 110 degree angle over 8.5. Okay, so that means r is going to be equal to, let's see, if we cross multiply and divide, then r would be equal to sine of a 35 degree angle times 8.5 divided by the sine of a 110 degree angle. Okay, so that's what r is. So I would probably type that in and store that value in r. Okay, so now back to our formula for the area of the composite figure. That means this value, this r, needs to go here and here and here. Okay, so once we type r in, and we can do all that calculation in one step, our area turns out to be 29, whoops, I'm going to do that in blue, sorry. Our area turns out to be 29.1 meters squared. Okay, again, I would highly recommend that you have stored r. You've done this calculation, punched in your calculator into Desmos, stored it in r, and then you can just type r into this calculation to find the total area. All right, so now let's tackle number 14. It says the following diagram shows a hexagonal pyramid where the base is regular and the vertex G is directly above the center of the base. Length AB right here is 6, so that's the one side of that regular hexagonal base is 6 centimeters, and the perpendicular height of the pyramid is 10. Okay, so let's start with the easiest stuff. Let's find the number of faces, vertices, and edges. Well, this pyramid would have 6 triangular faces and 1 base for a total of 7 faces. Vertices, let's see, there's going to be, there's going to be 1, 2, 3, 4, 5, 6 around the base, and then that 7th one, the vertex. So there are 7 vertices. And then edges, there's quite a few edges. So let's start from the bottom. So there's 6 edges around the base. And then there's these 6 edges vertically. And I guess 6 plus 6 is 12. So there's a total of 12 edges. Okay. So now we've got the faces, vertices, and edges. Now let's go to part B, where we're going to find the volume of the pyramid. So to find the volume of the pyramid, we're going to take 1/3 the area of the base times the height. Okay, so we need to figure out 2 things: area of the base and the height. The height, where we were told is 10, so we already know what that is. So now let's talk about how we're going to find the area of this base. Well, there are different ways we could go about this, but I'm going to kind of base it on what we've been talking about most recently in class. So I'm going to draw a bird's eye view of the base. That's supposed to be a regular hexagon. And to find the area of that base, what I'm going to do is I am going to draw a central angle and focus in on this yellow triangle, I'm going to find the area of that yellow triangle, and then I'm going to multiply it by 6 to get the area of the whole base, okay? And again, there's other ways. If you would recall from your freshman year in geometry, finding the area of a regular polygon, there's other ways we can do this, but I'm just trying to keep current with what we've been studying most recently. So to find the area of that base, well, let's first of all, we know that this side measures 6, whoops, let me get a pen here. We know that the edge measures 6 centimeters. We were given that. Now, this central angle, okay, there would be 6 of them, and all 6 central angles would total 360. So 360 divided by 6 would give me a 60-degree angle, okay? Then let's talk about finding one of these angles, okay? Now, from freshman geometry, you would recall that to find the sum of all of those interior angles, we would take, keep using the wrong pen, we would take the number of sides minus 2 times 180, and 4 times 180 is 720. Then if I take 720 and divide it among those 6 angles, I'm going to get 120. So this angle with the red arc is 120 degrees. So is this angle. But this radius here is going to bisect that angle, which gives me a 60-degree angle here and a 60-degree angle here. So I'm looking at an equiangular triangle, which is also equilateral. So I can call this radius 6 centimeters and this radius 6 centimeters. So now that I know 2 sides of the yellow triangle and an included angle, I can find the area of that one triangle. So area, I'm going to call this, let me give it a name. Let's call it A, B, C. So let's find the area of triangle ABC is going to be 6, oh no, not 6, I need the 1/2. Hold on. It's going to be 1/2 times 6 times 6 times the sine of that included angle, which would be the sine of a 60-degree angle, okay? So now, that would be the area of one triangle, but this hexagon would be made up of 6 of those, okay? So back to the volume of the pyramid. We're going to take 1/3 times the area of the base. Well, the area of the base is going to be 6 times 1/2 times 6 times 6 times the sine of a 60-degree angle, okay? So all of this, okay, let me highlight. So all of this, remember, was right here, finding the area of that one yellow triangle. So what do I have here? I have the 1/3 times the area of the base, which is 6 of those yellow triangles, but I still need to multiply by the height. Remember, we were told the height is 10, so I'm going to multiply that by 10, okay? So do all that arithmetic in one step on your calculator, and then to 3 significant figures, or exact, I can't remember if this was exact, I think it's going to be to 3 significant figures, 312 centimeters cubed. Okay, so there's part B, all right? Now, let's move on to part C. And part C is going to be a little tricky because we're asked to find the surface area of the pyramid. So the surface area of the pyramid, okay, this pyramid is made up of, it has a base, that hexagonal base, plus it has the 6 triangles, okay? So we already know what the area of the base is. We've already figured that out. So finding the area of the 6 triangles is going to take a little bit of work. So let's do this. Let's go ahead. I'm going to draw in the diagram. I'm going to draw that height of 10. Remember, a height of 10. And then also I'm going to draw this radius, which we knew was 6, okay? So using Pythagorean theorem, I can now find this lateral edge. Let me highlight it. We can find this lateral edge because it's the hypotenuse of a triangle with legs 10 and 6. Okay, let me write that a little. Let me write these so you can read them a little bit better. So this was, oh nuts, hold on. Okay, so this height was 10 centimeters and this radius of the base was 6 centimeters. We found that out from previous work. Okay, so Pythagorean theorem, I'm not going to take the time to do that right now, but if we did the Pythagorean theorem, we would find out that this hypotenuse is going to be the square root of 136, okay? And remember, the hypotenuse squared is the sum of the squares of the two legs. Okay, so now, let me draw my triangle. So I'm going to highlight what triangle I'm going to draw. Let me shade it. So this triangle, which is one of the lateral faces, okay, you redraw that triangle. It looks like this. Oh, nuts. I meant to use a pen, not a highlighter. Okay, it looks like this. It's going to have two sides that measure the square root of 136 and 130. Sorry, it'd help if I could write so you can read it. Okay, 136, and then it's got this side that is 6 centimeters. Remember, we were told in the very beginning that that these edges are all 6 centimeters. So what I'm going to do right now is I'm going to find this angle theta, and once I have found that angle theta, then I can use the formula for the area of a triangle. I can take the square root of 136 times, or 1/2 times the square root of 136 times the square root of 136 times the sine of this angle. So to find theta, I'm going to have to use law of cosines. When you know three sides, that's the time to find law of cosines. So theta is going to be cosine inverse of, if you recall, we've done this a bunch of times, it's going to be cosine inverse of 6 squared minus, I'll just go ahead and write the square root of 136 squared minus the square root of 136 squared, all divided by -2 times the square root of 136 times the square root of 136. Okay, that's just law of cosines like we have done a whole bunch of times. So what I would do is I would do that calculator, or do that arithmetic on a calculator, and then store that value. So now to find the area of this triangle, okay, the area is going to be 1/2 times the square root of 136 times the square root of 136 times the sine of angle theta that we've already figured out, okay? So that's going to give me the area of one of those faces, okay? So back to the surface area of the whole pyramid, okay? I'm kind of running out of room here. Okay, remember capital B? Capital B would be this right here, 6 of those yellow triangles, plus I need 6 of these. Okay, so let's call this, let's give this a name. Let's call it, I've already used capital B, so let's just call it little b, okay? And I'm going to call this little a, okay? So to find this total surface area, we will take, let me change colors here. We're going to take the area of the base, which I'm calling little b, that's 6 of those yellow triangles, plus 6 times little a, because remember little a was just one of these lateral faces, okay? So if you've already had those variables stored in your calculator, you'd want to use exact values, but if I take the area of the base, let's see, area of the base plus 6 times those lateral faces, then your answer should turn out to be 296, let's see, 296 centimeters squared. This was surface area, so you need to make sure your units are in centimeters squared. Okay, now if that wasn't fun enough, let's do letter D, which says find the angle between face AFG. So that's this yellow, sorry, not yellow, this red triangle, and the base of the pyramid. Okay, so let's erase this. Okay, and I'm going to re-highlight that red triangle. And then I'm going to draw the altitude of that red triangle, which also happens to be the slant height of the pyramid, okay? So now, if we look at this triangle, we're going to call this L. I know that this much is 3 because the whole base, the whole edge is 6. And remember from previous work, I know that this lateral edge is the square root of 136, okay? So using the Pythagorean theorem, we can find L. Let me just go ahead and redraw that triangle down here. Okay, we've got L, square root of 136, and 3. So the square root of 136 squared is equal to 3 squared plus L squared. So that means L is going to be equal to the square root of, I'm just going to go ahead and write 136 because the square root of 136 squared is 136 minus 3 squared. Okay, that's what L is. And now let's see if I can draw, I'm going to go back, let me get a different color, how about black? I'm going to go back and draw that height, remember that was 10, and then I'm going to draw this edge right here, okay? So that triangle, this triangle that I'm highlighting in black, let me redraw that, I'll draw it over here. So I've got, this is the height of the pyramid, and then I've got the distance from the center of the base to the center of an edge. And then I've got L, the slant height. L, the slant height. Okay. So I guess I didn't finish calculating L. So L is going to be the square root of, let's see, 136 minus 9 would be the square root of 127. So L is the square root of 127. Oh gosh, that's not even close. 127. Okay. And then remember, we also know that this side is 10, okay, because this is the height of the pyramid. And we were asked to find this. I'm going to call this theta, okay? That would be this angle right here, okay? That's theta. That would be the slant height and then the base of the pyramid. Okay, so since this is a right triangle, okay, to find theta, I can use the opposite side and the hypotenuse, okay? So that means theta is going to be sine inverse of opposite over hypotenuse. So that's going to be 10 over the square root of 127, okay? So grab your calculator, make sure it's in degree mode, and theta turns out to be, to 3 significant figures, 62.5 degrees. Okay, so that was our answer to part D. All right, so that was a pretty tricky problem, but it's a good problem because it did review a lot of the things we've been talking about for the last few weeks. All right, so if you have any questions, just send me an email or you can ask me in class. And I hope this video was helpful to you, and I'll be talking to you soon.